Welcome back everyone. In this lecture I will continue the proof of Engel's theorem. Okay. We have actually seen various versions of Engel's theorem. So, except to one proportion I have proved everything. I will recall what is that proportion and then I will give you proof using the invariance lemma. So, what is that proportion? So, let G being linear Lie subalgebra of some GL of V. So, we assume that V is a non-zero finite dimensional vector space over C. Okay. So, assume that all elements of G are nilpotent linear transformations. Nil transformations of V. So, then what we claimed, so you can have there exists a vector V in capital V such that it is annihilated by all the elements of G. Okay. We saw that using this fact one can actually establish a basis of capital V such that each element of G with respect to that basis can be represented as strictly upper triangular matrix. Okay. So, let us see how one can prove this statement. So, here is the proof. So, first we need to make some observations about our Lie algebra, okay, and then we will actually able to proceed by induction on the dimension of G. Okay. So, suppose so here is the thing. Okay. If we are able to prove G is actually nilpotent, so let us do some work backward. Okay. So, let me do it in the side. So, this is some work backward. So, what it says, okay. Suppose G is nilpotent, okay, Lie algebra. So, then what happens? So, then you can see that this bracket G will be a proper subspace of G. Okay. So, it is an ideal, it is also should be proper. Otherwise, what will happen? The derived algebra will be equal to G. So, then you can easily check that any other lower central series element will be G. So, then G will be never nilpotent. Okay. That is why we should have the bracket G is properly contained in G. So, now if this is true, then you can take any A which actually contains this G, okay, and we can also choose this A to be codimension 1. That means, the dimension of A plus 1 is G. Okay. So, dimension of A plus 1 is dimension of G. So, now if you take any A which is a subspace of this bracket G, so which we can actually do. So, since G modulo bracket G is abelian, so using this ideal correspondence, so you can see that this A must be actually ideal. So, this A is an ideal in G. Okay. So, this is always true when actually you have this nilpotent Lie algebra. Actually, this is indeed true even for solvable Lie algebra, because again if G equal to its derived algebra, then it cannot be solvable. But unfortunately, we can't make this choice of A. So, once you make actually this choice of A, now using the induction, the proof is very clear. Okay. Let me complete the proof with the choice of this capital A. So, what is going to happen? You can choose y which is not from A. So, then G can be written as A plus Cy. Okay. So, now since A is an ideal, so now A being a subalgebra of G, G is nilpotent Lie algebra. So, that should imply A is also nilpotent. Okay. So, that means if we take if we consider our hypothesis. So, what is our hypothesis? So, this hypothesis we are doing it for linear Lie subalgebra whose elements are actually nilpotent linear transformation. But if you slightly change this hypothesis to only the nilpotent linear Lie algebra, so then you can see that this A is actually nilpotent linear Lie subalgebra acting on this capital V. So, by induction on by induction on the dimension of capital A, you can see that. So, this space W which is those vectors in capital V such that x v equal to 0 for all x in capital A will be non-zero space. So, this is just by induction. Okay. So, now using our this invariance lemma, you can see that this W is G invariant. So, that is what invariance lemma says. So, in particularly W is Y invariant. Okay. So, now if you assume that all the elements of G acts as nilpotent linear transformations. So, that is also you can add it in the hypothesis. Okay. So, then you can see that this Y should act on W as nilpotent linear transformation. So, that would imply that this Y should have some non-zero vector W inside W such that Y W is 0. So, that implies this W is killed by all elements of x in G, because G is nothing but capital A plus C y, and this W in W is already killed by capital A. So, this Y also kills this small w. So, this small w is killed by all the elements of this. So, this argument actually tells you as long as you are able to actually come up with co-dimensional 1 ideal inside G, then you are done. Okay. But unfortunately, we can't use this G being nilpotent, because that is what we are aiming to prove. Okay. So, we have to actually go around and then prove the same fact using some other method. So, what we will do, we will actually kind of use again induction on the dimension of Lie algebras or vector space to conclude the same thing. So, for that so here is the step 1. So, now you can forget whatever I said. So, that is all, this work backward is done. So, now what we do, we start with the Lie algebra inside GLV that satisfies our hypothesis. What is our hypothesis? Each element is nilpotent linear transformation of V. Okay. So, now what we want to do? So, we will actually start with what is called this maximal Lie subalgebra. Okay. So, that makes sense. Now, I can always take a maximal Lie subalgebra of G. Okay. So, what we do, we actually claim that this A is indeed an ideal, okay, and the dimension of this A must be 1 less than dimension of G. So, that is what our required ideal that we were actually looking here. Okay. So, how do I actually get these statements? Okay. So, for that what we do, we actually consider this quotient space. So, we do not know whether it is actually again Lie algebra, but quotient space makes sense. Okay. So, what you do, you take this quotient space, so which is, we call it G bar, which is G modulo capital E. So, this is just a quotient space. Okay. We do not know anything about this space. So, now what we can do? So, we can actually define a linear map, okay, call it phi So, from this capital A to this GL of this G bar. Okay. How this map is defined? So, this capital A, because it is a subalgebra of this G. So, this capital A will naturally act on this G mod capital A. So, that is the action we are talking about. So, in particularly given A, we define this phi A. So, this phi A is a map, okay, on G bar to G bar. So, how it is defined? Phi A of some x plus A, okay, phi A of some x plus capital A is defined to be. So, you use this subalgebra action. So, you take A x plus capital A. Okay. So, this is the action. So, why this is actually well defined? Let us check that it is well defined. Suppose x plus A is same as y plus A, then that would imply that x minus y is in capital A, and that would imply that A x minus y, the bracket is in capital A, as A is coming from capital A and A is subalgebra. Okay. So, that means this A x minus A y, so that is in capital A. So, that would imply that the bracket A x plus capital A is same as A y cap plus capital A. Okay. So, this actually tells us this phi of A is well defined. Okay. So, now once phi is well defined, it is not hard to see phi is actually linear map. So, I will leave it to you to check. Okay. This is something easy to check. So, what we will actually claim, this is indeed a Lie homomorphism. Okay. So, the claim phi is a Lie homomorphism. So, if phi is actually Lie homomorphism, that is actually just follows from Jacobi identity. So, let us just check. Okay, this is not a deep thing. So, for A B in capital A, okay, so what we do, we just compute phi of A, phi of B on this x plus A. So, we need to say that this is exactly bracket phi of bracket A B acting on x plus A. But what is this? This is by definition, you can see that phi of A, phi of B minus phi of B, phi of A applied on x plus capital A. So, which is equal to A bracket B x plus capital A minus B bracket A x plus capital A. Okay. So, if you take it out, then you can see that this is A B x minus B A x plus capital A. Okay. So, this is a quotient, but if you use Jacobi identity, this element that is here. Okay. So, that element using the Jacobi identity can be rewritten as follows. This is just A B x plus A. Okay. So, what is that? If you just unravel the definition, this is just phi of A B applied on x plus A. So, this proves that phi of A B is nothing but phi of A, phi of B. So, this verifies phi is actually linear Lie algebra homomorphism. So, in particularly I can talk about this phi of capital A. So, this is actually a subalgebra of this GL of G bar. Okay. So, that is what we wanted. Now, you can see that the dimension of this phi of A is definitely less than the dimension of G. Okay. So, because A is being a maximal subalgebra, so that is actually maximal means proper. Okay. Because of that we have this is literally smaller. Okay. So, now what we can do, so we have this phi of A which is a subalgebra of this GL of G bar. Okay. So, now we can actually use induction hypothesis if you know that phi of small a is nilpotent linear transformation of this G bar for all A. Okay. But so what is, so we want to use induction. Okay. Now we want to use induction on what? Induction on the dimension of this G. So, in particularly, so I want to use induction on phi of A. So, to use induction on phi of A, go back to our hypothesis. What we need to actually check? Our G should have all nilpotent transformations, okay, then only acting on some space. So, then only I will be able to use induction. So, for that I need to check this phi of A as on operator on this G bar must be nilpotent. So, if I check, so this is what we need to check. So, then we can actually say that we can apply induction on phi of A. But what is phi of A? Phi of A, if you think about it, this is given on x plus A is nothing but what? It is bracket A x plus A. So, basically phi of A is induced from add A. Okay. So, add A on G, okay, maybe. So, but A is actually, so A in G is nilpotent transformation, that implies add A is nilpotent, okay, that we have already seen. Add A acting on G, okay. So, let us say I put G here, add A acting on G is nilpotent. So, but since this phi of A is induced from add A, so phi of A also must be nilpotent, because this is just a induced map. Okay. So, that tells us that all these elements of phi of A, okay, where A is coming from capital A, this consists of nilpotent transformations of this G bar. So, now we can use induction on this subalgebra, okay, phi of A inside GL of G bar, because G bar is also smaller dimension. So, if we use induction, then what we get? We have to get some x that is killed by all this phi of A. Okay. So, take non-zero element x, okay, that x should look like some y plus A inside your G bar. Okay, this is a non-zero element. So, that means y is not in A, such that this phi of A on this y plus A should be 0. This is true for all capital A in capital A. But what is phi of A y plus A? That is A y plus A. So, this should be 0. So, that means the bracket A y is inside capital A for all A in A. Okay. So, in particularly if you take this A tilde, so which is span of this y and then capital A. So, then this actually becomes a Lie subalgebra of G containing capital A. Okay. So, but A is maximal. Okay. So, that would say that A actually must be equal to A tilde, or A tilde must be equal to, so A is being maximal implies, and y is also not in capital A by the choice. Okay. So, this is non-zero, that means y is not in capital A. So, these two things implies this A tilde should be equal to G. Okay. So, what we have done, we have proved that G is equal to A direct sum some one dimensional space. Okay. So, it is clear that using this equation, this capital A, okay, must be ideal inside A tilde. Okay. So, this is the equation. So, what this equation says? So, A is already a subalgebra. So, the only element that is not in A, which is in A tilde, okay, as long as base is concerned, is this y, but this y is actually kind of leaves this capital A invariant. So, add y in leaves capital A invariant. So, that it is immediate that A is ideal inside A tilde. So, that implies A is ideal inside G. Okay. So, this way we are actually able to construct ideal of codimension 1 inside G using our information. So, now once we have constructed this, then as I said, so you can actually construct this subspace. So, because A is ideal inside G, look at this W, which is those vector in capital V such that that is killed by the vector is killed by all x in capital A. So, since A is an ideal, so this W is invariant under G, okay, using the invariance lemma. So, now this G is nothing but A plus C y. So, this y must leave W invariant. Okay. So, that will imply that y will act on W, but y is given to be nilpotent element. Okay. All elements of G acts as nilpotent transformation on capital V. So, in particularly y restricted to W is also nilpotent. So, that implies there will be a vector some W, small w, such that y W will be 0. So, that is the W that we want, okay, because already A W is 0 for all A in A, and then y W is also 0. So, that implies x W is 0 for all x in G. Okay. So, that is the W that is wanted in the proportion. So, this proves actually that our proportion. So, with this proportion we have actually completed the proof of Engel's theorem. Okay. So, the main important okay, thing about Engel's theorem. So, let me recall that to verify G is nilpotent, it is enough to verify all the elements of G are okay, add nilpotent or not. So, that is one characterization, and from that one can see that if G is nilpotent, okay, so then what one can prove. So, it is G is nilpotent inside some GL of V. Okay. So, then okay. So, sorry, what we have proved? We proved that so we want to get actually a basis for any nilpotent thing. So, let us start with arbitrary thing and then see what we are getting. So, we want to get start with G, let us say arbitrary nilpotent Lie algebra. So, then what we know? Then we know that any element of G is add nilpotent. Okay. So, that is very clear. In particularly we can use the Engel's theorem E2 dash version for this add G. Okay. So, add G is sitting inside GLG. So, now there exists a basis B of G such that this add G with respect to that basis sits inside n of dimension G comma C. Okay. So, that is what we have proved so far. So, for any arbitrary nilpotent Lie algebra, okay, so you can find a basis B of G such that, so all the elements in add G look strictly upper triangular matrices. But of course, the elements that comes from the center they all act 0. So, they do not play any role. Okay. So, if you include the elements of the center as well, okay, which only contributes to the 0. So, this actually can be replaced as follows. So, you take only add x, okay, with respect to this basis where x is now you can take it to be any x in G. So, this is also inside your strictly upper triangular matrix, because if x is coming from the center add x will be 0. So, we do not need to worry. Okay. So, let me actually give you one interesting characterization of nilpotent Lie algebra and then I will stop. Okay. So, this can be now proved using this Engel's theorem. Okay. So, this is actually true only for the complex Lie algebra. Okay. Let us take it to be complex. So, G is just arbitrary Lie algebra over C. Okay. Again finite dimensional we have to assume, okay, always that is there. So, here is one of the characterization. Okay. So, what is this characterization? Maybe you can call it E3. So, this is actually says G is nilpotent if and only if every 2 dimensional subalgebra of G must be abelian. Okay. So, let us prove this. So, for the if part okay sorry. So, G is nilpotent will imply that any subalgebra of that G must be nilpotent. Okay. So, in particularly if you start with the 2 dimensional subalgebra, so then by the classification of 2 dimensional subalgebra we know that, so let us say G dash is 2 dimensional subalgebra, then by the classification G dash either has to be abelian or isomorphic to non-abelian 2 dimensional. But the thing is we already saw that this 2 dimensional non-abelian is soluble, but not nilpotent. So, that means, so this choice is not there because any subalgebra of a nilpotent Lie algebra is nilpotent. So, that means G dash must be abelian. So, this is fine. For the converse part, assume that all 2 dimensional subalgebras must be abelian. So, we have to prove G is nilpotent. To prove G is nilpotent, it is enough to prove that if you take some element x inside G, that is actually the add x of that must be nilpotent. Okay. So, let us say add x is not nilpotent. If add x is not nilpotent, then what will happen? So, it will have actually some eigen value which is non-zero. If all the eigen values are 0, then add x must be nilpotent. So, you can assume that it has non-zero eigen value. So, in particularly there will be a eigen vector corresponding to that eigen value, let us say lambda. So, the bracket x y will be lambda y for some lambda non-zero inside C and y in G. So, now look at this equation. So, this bracket x y is being lambda y. So, by actually normalizing it back, you can see that lambda inverse x is y is just y. So, you can replace x dash by lambda inverse x and then y by y, y dash by y, then this span of x dash and span of y dash. So, this will form a two dimensional non-abelian Lie algebra. Okay. Why? Because it is easy to check, it is actually a subalgebra, because bracket x dash y dash is just y dash. Okay, it is obviously non-abelian. So, this proves that there exists a non-abelian two dimensional subalgebra. So, which is contradiction from the hypothesis. So, G must be nilpotent. That means all adx must be nilpotent. That implies using Engel's theorem, G is nilpotent. Okay, I will stop here. We are running out of time. So, I will continue in the next class with the proof of Lie's theorem.